All right, good morning, everybody. I'm very pleased to see so many people after the conference dinner on the first track. We will start with something lightweight, like C++ reverse engineering for the morning. Gal is our next speaker, and Gal, the stage is yours.
Thank you. So my presentation is called When Virtual Health Freezes Over, Reversing C++ Code. So first I'm going to start with who I am. My name is Gal. I'm a reverse engineer and work as a security researcher at Viral Security Group. I'm a spare time, I also like sewing. And this is my own private research that I've done at home in my spare time. So there is a few parts for this presentation. There will be the research part that I'm going to talk about reversing C++, the C++ internals. I'm going to show some concept of why C++ is so hard to reverse. And the second part is going to be my tool that I've written. I'm going to talk about either Python and the tool that I wrote that's called Virtualer that helps with the virtualization of C++. So what is the problem? Reversing C++ is hard. Let's see some examples. I just want to mention one small thing. This all, what I'm going to show is MSVC compiler and not G++. There is some differences between the compilers. So if we want to adjust my tool afterwards, it's possible. But for now, it's only support MSVC. So the first thing I'm going to talk about is dynamic object creation. So in this code, you can see it's a simple code. There is one function called, one class called the father A. It has one int member, which is the age, and two virtual functions. One is getAge, and the second one is printAge. In the main, you can see that the object was created dynamically. The first part is the new. In this part, what happens is that we allocate bytes on the heap in order to create our object. In this case, 8 bytes. In this case, 8 bytes, and the function operator new is called. Father1 is the name of the class. And here you see the constructor that was called. It's named father1 constructor, and after this function was called, the return value is the pointer to the object. So let's summarize it in a small table. There is two actions happen when we create an object. The first one is the allocation, the heap allocation, and the second one is the construction call. So constructor call, and you can see in the right side you can see the assembly, and in the left side you can see the action, as we've seen before. But we want to know more about the constructor. So here we have a small assembly part from a constructor, a basic constructor. You can see the first 4 bytes assigned to the Vtable in the object, and the second 4 bytes, in this case, assigned to a member. In this case, it's a float member. You can see it by the XMMF0 register, which is related to floating points numbers. And in case there is more than one member, what happens is that you have 4 bytes for Vtables and then all the members of the relevant object. So we talked about objects and about constructors, but the main purpose of this talk is Vtables. And this is the main thing in C++. So how does a Vtable really look like? So you can see here we have 2 functions, father0 and father A. Father A inherits from father0. And there is a few functions that are the same for both of them. Since father A inherits from father0, it means that it also inherits the functions that was implemented in father0. But in this case, you can see print hello me, which is a virtual function that was also implemented in father A. So in this case, we have, you can see down there, down in the slides, you have the tables that show the Vtable. So let's start with father0 Vtable. You have the print hello, which is the function implemented in father0. And then you have the print hello me. In this case, it's the function that was implemented in father0 also. But if we look at father A Vtable, you have print hello, which was not implemented in the code in father A, and then it's just inherit the function from father 0. So in this case, both of those functions are the same. But we have the second function, which is print hello me. In this case, father A implemented this function. So in order to, so the Vtable is different, because now this function is not the same as father 0 Vtable, as father 0 function, because both of them implemented this function. The third function you can see in VA, father A Vtable, is print num, which is a function that was only created in father A, so this is the reason you can only see it in father A. So this is in general how the Vtable look like. It sounds a little complicated, but if you look at it in IDA, this is just an array of functions, just a list with functions, and this is how a Vtable really look like. The problem is that you don't really know what, when you do a virtual call, you don't really know what function was called. Because as you can see here, you have three important instructions that I marked. The first one is the assignment of the Vtable to EDX. This is the first instruction that is important. You take the first 4 bytes with the Vtable from the object that here is stored in EAX and move it to EDX. So now EDX has the pointer to the Vtable. The second instruction that I marked is the assignment of the function from EDX, the Vtable, to EAX. In this case, you have offset 4, which means it's the second function inside the Vtable. And the third instruction is call EAX. Here, if you can see this code, you don't really know what function was called, because you can't see the Vtable and you can't see the functions. You only see registers and you know they store some kind of an address, but you don't really know what address. So this is a very big problem as reversers, because all the virtualization that you have in C++ must be researched dynamically. And a lot of time you need to run your code again and again in order to get all of those things. So one more last big issue that we have is also multiple inheritance. We talked about inheritance, that one class can inherit from a different class. But what happens when one class inherits from 2 different classes? So in this case, it's a little, there is a lot of code here, but I'll explain it like what happens here. We have two classes, father B, father A, and class C inherits from both of them. So there is a lot of problems that happens with multiple inheritance. I'm only going to focus on one thing, that's showing you how it looks in IDA and how it looks after it was compiled. So in this case, we have 2 virtual functions that are both implemented in B and in A. But in C, we have one more function called foo2 that was only created in class C. So how multiple inheritance really look like? We talked about the object and how the object looked like when we create it. But now we have multiple inheritance. And this means that we have 2 fathers for the same object. So in this case, what happens is we create father A object and then father B. And just at the end, we add all the members of the current son's object, which means in case we have C. So the first thing that happens is we create the 4 first bytes of a Vtable for C if it only inherits from father A. Then we add all of the A members. The second thing we are going to have is the Vtable for C if it only inherits from B. And then we have all the B members. And the third part is the C members. Because C is also an object, it has its own members, then we have all the members that C has. So, okay. So one more thing is the function calls in multiple inheritance. It might look very complicated because there is lots of objects here and like all the relationship between them. But one simple thing is that if you have to inherit 2 fathers, you need to explicitly say which father you're going to use, which function you need to use. So as you can see in here, in the highlighted part, you explicitly said father A and the function name. And as you can see in the assembly, the name of the function is exactly the name that's supposed to be called. It's not a virtual call, it's just a call. So in this case, it's easier sometimes to look at because you can just see the flow of the program. The problem comes when you look at the fifth call, which is foo2. It's a virtual call that was implemented in C. So in here, you can see in the last instruction, call EAX. This is an address that we cannot know statically where it points to. So as you might have seen, it requires a lot of work to reverse C++. You have lots of stuff you need to consider, and you have lots of stuff you need to work on and know before you even start to look at the logic of a program. I want to make it fluffy. So I wanted to use tools that are really easy to use them, but it's also very powerful tools. So what I chose is IDA, Python, and IDC. It was trivial for me because I already knew them from before. These is tools that are only, they are IDA. They was created by IDA Pro, and it can be used to program some automation for reverse engineering. So IDA Python is easy peasy to write because it has lots of examples because, well, everyone likes to write code in Python. And then there is lots of examples. The code is very easy to write because it's also, you don't have to think about all the things that C needs to be you don't need to think about all the things that you need to think about if you write in C. And IDC is more like a C programming language that has its own compiler that IDA created. It's more extensive. It has more stuff because it's more low level, so it's connected to the APIs that IDA provides. But it's hard to know how to write stuff. There is no documentation. There is a little documentation, but there is no examples. So you really need to go deep into the files in order to write IDC. So this is how it all began. I wanted to write something that will help me reverse C++. Because when I reverse C++, I had all this virtualization problem, and I had to write all the structures by myself, and I said, there must be some way to automate all of this process in order to make it easier for me as a reverser to continue and go into the logic instead of going into the framework for how that stuff works. So I said, okay, fine, I'll find a way. So this is how it began. I took a whiteboard and just write everything I wanted and add everything that I thought about to the board. And then I also got a nice print, a nice painting here from one of my friends. So then I continue and came up with Virtualer, which is the tool that I'm going to speak about. So the first thing I thought about is automating IDA tracing. Because IDA already has tracing, we can maybe take this and use IDA Python in order to automate all of this process and create automated trace. And so what I want to do is create trace breakpoint on the virtual calls and then parse the trace file that was created, and that's it. But there was a problem. Since tracing might sound like a good solution, but it didn't give me a real-time solution. You need to finish all of the running and then just to manually press on the save the file, parse the file, and it's not what I wanted. It also gave me only the specific function that was called and not all the Vtable. You can only see one function. So it created problems that didn't give me the whole solution that I wanted. So I thought okay, fine, I may have some dynamic solution. I must find some solution for it. So I decided to taint backward, which means go backward in the instruction, look at the register's values, and then find the right assignment of the Vtable to the register. In the cases we've seen before, it was, for example, EDX, but it can be lots. It depends on a lot of stuff. And the second thing I wanted is to create structures of the Vtable based on the Vtable pointer. So I wanted to create the structure in IDA of the Vtable. And I also wanted to correlate between the assembly and the structure because I wanted a way to connect between them and see how they are really related. So the first thing I thought about is breakpoints. It's a good solution. It gives me an option to hook some places and now be able to run my code. So how you create a breakpoint. This is the basic thing in IDA Python. There is just one command. You can just write IDA API add breakpoint. You add the address, the number of bytes that you want for the breakpoint, and the type of breakpoint. In software, breakpoint, what I have here, is not really relevant because just in hardware breakpoint, you can add the number of bytes you want, but in software, it's not really relevant. So 0 is the default one, which means 4 bytes. So until now, it sounds like nice. I just like add breakpoint. And the second thing I wanted is to look at the condition of the breakpoint, which I'm going to talk about now. So before we're talking about conditional breakpoints, I'm going to talk about how I want to hook the Vtable pointers. So at first, we want to find all the virtual calls, because we need to hook the relevant parts in order to get the Vtables. So this code is going through the code and search for virtual calls. It's not a very complicated one. I know there is a lot of code here, but I'm going to publish my tool at GitHub afterwards. So if someone is interested, you can just go and see what is there. So if I add breakpoints on the Vtable assignment, I can get the pointer to the Vtable and then get all the functions. This is what I thought about. So conditional breakpoint it was my way of hooking this code, because one of the things that IDA provides is conditional breakpoint. In every breakpoint that you have, you can add a condition, which means you can write code that if it was like correct, true, so the breakpoint is hit and break. But in case it's not and the condition is false, just continue. What I wanted to do is write code with a false condition that will always be false. So the breakpoint will never stop. But my code will still run. So it means I can hook places, run my code on them, and then just continue with the flow of the program. So when you run the code, when you run my tool, none of the user, which is the reversal, doesn't need to stop the program while it runs. It just can do stuff on the program, on your C++ program, and then on the background, your IDB is being filled with the comments, the structures, the Vtables, everything. So conditional breakpoint in IDA Python, there was a small problem, a small but annoying one. The conditions that you can write with IDA Python are only IDC. So it means that all I can write is conditions in IDC. So in general, I don't have problem with it. I can just write it in IDC. The problem was that all the functionalities that on the functions and the functionality I needed was in an idc.idc file that you need to include to your code. The problem is that in conditions, you cannot include files in IDC. So here, I can only do the basic stuff. I cannot create structures. I cannot correlate the structure with the assembly. And then, it's not what I wanted. I can just use the tracing for before. And I felt like I must find a solution. So I said, OK, let's dive to IDA Python and find a way to change the condition to IDA Python. So this is the code that set the breakpoint condition. I looked inside the code, and there is no reference to the language of the condition. It just add the condition. It doesn't have anything about language. So I wanted to change the language. So I thought, fine, let's try to look at IDC. It might contain something that will help me. So I looked in IDC. You have class breakpoint in IDC, and one of the attributes is elang, as you can see there on top. This is the language of the condition. So I thought, fine. If it's in IDC, I must find a place in IDA that also has this, in IDA Python. So what I found is in IDA API, which is one of the modules that of IDA Python. There is a elang attribute, but there is no function that changes it. So I thought, fine, I'll just create this class. I'll change all of the attributes manually, and then I'll have a breakpoint with the right language. So this is how you create a breakpoint with changing the language. In the marked box, you can see the changes I made. I created this object, and then I changed manually the bpt.elang to my self.elang. Which means this one is part of a bigger class, and this class has options for both conditions in Python and in IDC. The default option is that self.elang is Python, but you can, as a user who uses my tool, can change it to IDC. So So here we have a breakpoint that you can create with Python condition. So yay, this is like what we wanted. So the hook purpose. Now we have all the tools in order to create the hook. Because we have the places with the virtual calls, we have the places with the Vtables assignment. We also have breakpoints, and we also have conditions in Python. So what we want now is to write the hook. So as I mentioned a few times, I want to create the IDA structures of the Vtables. I want to connect the structures with the virtual calls in the assembly, and I also want to add comments both to the structure and the assembly. The last thing you want to do is to correlate the Vtable pointer with the struct. So I'm going to show more, as in the future I'm going to show exactly what I mean. The hook location. So the hook is a breakpoint, as I said, and it's located in the assignment of the relevant function into the register. In this case, it's EDX, and you see that EDX plus 4 is the relevant function. EDX contains the Vtable, 4 is the offset inside the Vtable, which means that the second function from the Vtable is being assigned to EDX. And this is where we have the hook. First, we want to get the Vtable pointer. So EDX contains the Vtable. We just need to get the value from EDX, and then we have the Vtable pointer. One thing that I'm going to just mention, you see here, this code that I wrote is IDA Python who creates IDA Python. This is why it looks a little weird. I just had variables with the register Vtable. In this case, EDX. It's from a previous code that I've written. And this part is only the hook itself. In order to write the hook, I need to consider all the variables that I already have from creating this breakpoint, which is the location of the breakpoint, the register that are involved, and the offsets. So in this case, we take the register and the offset, and we assign to pvtable and the right value, and to pv function address, the relevant function that was assigned to AX. This is how the hook looks like after we run the previous code. You see that when there was reg value, the reg Vtables, it's just changed to EDX, and the offset from before, I'll show you again. You see the offset and the register Vtable, it's changed to EDX and 4. So this is something that you're going to see a lot in the future slides, because I'm going to show you the code that creates the hook and not the hook itself. So, get functions from Vtable. So this is a very complicated part because you need to consider a few things. This is only a small part of this code. This gets the functions from before the function that was assigned to EX. It goes backward, take all the functions, and add it to a list. After this part, you also have a part that takes all the functions from the function to the end of the Vtable, and also append it to the list. Then you have a whole big list, which is very similar to a Vtable. Actually, it's a Vtable. It's an array of functions. So this is exactly what I create here. I create arrays of functions. So, yay, we have the Vtable. But we need to create the structures and everything else. So we want to create a structure. This is the command in IDA Python that creates structure. The structure, after we create it, looks like the right side in here. What I wanted to create is a Vtable underscore and then the address of the Vtable. So after you run your code, you can also go back and see where the Vtable was in the code. Okay, so we also want to add to the structure that we created the members. So all the members are the functions that we already added in the list, in the all functions list. In here we just go through the functions and add one member at a time to the Vtable structure. The functions I added v underscore and then the name of the function. I just wanted to show you here that you have two options. If the function's name that is taken is the function's name from IDA. So if you change, for example, a function to you research stuff, you reverse stuff, you decided that this function does calculate the size of something. And this is the name that you chose, so it takes the name that you've written. So it's not only taking addresses, it also takes the names of the function. So it's really easy as a reverser to look at it afterwards and see what you have. And this is what I mean. For example, this is a structure that was created, and this is how the structure looks now. So here you have the vtable and the address, and the members underneath them, you have, for example, here you have two functions. One is a function with a name that you, as a researcher, have changed in IDA, and the second one is a default function name that was not researched yet. And then you have a nice structure, but not good enough. Like, we need to make it fluffier. Because we also want comment, we need to correlate everything, so we still have some work to do. We can add comment to the structure, but we need to think about two things. If you have a function, it could be called from more than one place. So you need to add all the places that this function was called. So this is also something that I considered when I wrote everything. The first part is when you don't have this function was not called, we just write a comment, but in case that there was already a call for the function, I add all the addresses so you can see all of them after the program is stop its run. So this is the part that add new comment and add functions name to existing comment. So this is the code in IDA Python that creates the hook. And the second thing that you want to do is to add comments to the assembly. Because we cannot only write comments on the structure, we also need to write comments on the assembly itself. So what I do is just like go to the function assignment and just correlate it, write from which vtable the function was assigned. So then you have in the structures, you have the virtual calls that's relevant to the functions in the structure. And in the assembly, you have all the vtables and the functions in the vtable structure that are relevant for the virtual call you are looking at. And one last thing to add, we want to create structure offset and false condition. So the false condition is what I said. You want to stop the code from stopping. So you have a false condition, and then the code that I wrote is being run, but the breakpoint is not being stopped. It's not being braked. So it's a breakpoint that doesn't really break. The second thing is the structure offset. You can say that a specific address register or whatever is related to a specific structure. This is a tool that IDA provides, but then you can look at the assembly and see which function was called from edx plus 4, for example. It will not look like that. It will have the function name. So we also need to add this ability to the code. So this is a simple line that can just do it. And now the hook is finished. Yay, we can continue. So this is how the hook looked like. It's small, but I just want to show you, like, it's giant. There is lots of stuff inside, and I didn't even show all the stuff. And this is how the hook, which is just the condition inside, is. So this is how the code looked before. It's just like assembly. You have virtual calls that are marked in yellow, and this is how it looked before. It's really hard to look at it. This is after you run the tool. You have the vtable structures that were created. You see there is two virtual tables here with two functions in every virtual table. In this case, this is the code from before that we've seen with father A and father B. Also, you can see there is comments that every function has like was called from and an address. And this is the disassembly after the tool was run. You see that there is comments inside the assembly and also oops, sorry. Sorry. Okay, fine. I just wanted the laser. Okay, so we will deal with it like that, I guess.
This one and the test presenter, this is the green lady.
Okay, green laser is okay. Okay, fine. Wait, yes. Yay, it works. So, okay, here you have, okay, here, this is what I said about structure offset. Instead of edx plus 4, here you have edx plus vtable and the name of the function that was called. So it's easier, just see the function. You don't need to use this weird offset that says nothing to us. It just has the name of the function that we use. It also adds the comment from the vtable, and then you can see that this address and this address here, which is the virtual call, are the same. Also, in the virtual call, you have the vtable structure is vtable 127 whatever address. So you have all the correlations between the code, the assembly, the structure. Everything is now connected, and now all you have to do is look at the code. You already has all the flow, and just start reversing. So, but there is some stuff that I wanted to add, and this is what I want to do in the future. The first thing is it's only the vtable, and the object is not created automatically, which is also a big part of C++, but it's possible. So the second thing I'm going to do in the future is add the object. So you also have automatic creation of the object. And the second thing is that if you have a function with strings inside, with calls, so maybe you can change the name. So inside the structure of the vtable, you will also have the names, the relevant names. Instead of sub, underscore, and an address, you will have maybe something related to the strings inside or to the calls inside. And so this is two things that I thought about adding. And thank you.
All right, any questions? Second row. I'm glad that it's second row.
Have you thought about combining this with symbolic or concolic execution to improve the vtable discovery process?
So what happens, like I said, it uses the names inside the IDB. So if you have symbols connected to the IDB, it already takes all the names with the symbols. Okay, so so yes. If you want, I can explain you more, like how and stuff.
More questions? Yep. First row.
Do you plan on supporting other platforms or like instruction sets?
So now it's 886. In the future, I might add more stuff. For now, I want to focus and make this 886 MSVC tool like the best it can be. And in the future, after, I'll be like extremely satisfied with how it looks like because I'm kind of a perfectionist, so it's a thing. And so then I might add more architectures and more compilers.
Okay, thank you.
More questions from the first or second row? Yes.
Have you looked at how different the register allocations are for other compilers and how easy that would be to just like kind of abstract away?
So I know the differences. There is a small differences, but you can't use it like as it is. It's just a small changes, not a lot of them, but there need to be some adjustments. I mean, between G++, for example, and MSVC, it's like different, but you can do it. It's feasible.
More questions? More questions? Last row? No? Okay, then thank you, Gal.
Thank you.
Nice talk. Thanks again. We're going to continue.